That's the pattern, that's not this one.
All right, guys, let's get started. Today we'll do AC circuits. What does AC mean?
Alternating current.
Yep. Okay. So let me. Okay. So here's an AC source. Okay. Here's how you produce. Here's one way of producing AC voltage. Here's a. This is a generator. Here are magnets. Here's a wires. And if you turn this wire in between magnets, the flux through this loop changes, and that induces a electric field, and that produces this voltage. Okay. If the wire is connected to the outside brushes like so, this is the voltage you get. All right. And here, as you can see, this is an AC voltage. Now, how do you turn this wire? In a windmill, the wind is turning the blades, which is turning this wire. In the dam, the flowing water is turning this wire. In a coal power plant, you burn coal, produce steam, the steam is turning this wire. In a nuclear power plant, you split nuclei, boil water, the steam is turning this wire. Now, in a windmill, the wind blows at different speeds. So So if you turn this, what you're getting out of the wall is 60 hertz. That is, you're getting 60 wavelengths each second. In a windmill, the wind is blowing at all kinds of variable speeds. So it turns this at variable frequencies. So you're getting a variable signal. The frequency is changing. So what you have to do is, in the windmill, you convert this to DC, then back to AC at 60 hertz. Okay? But all that's technical details, and we'll talk about how to convert this to DC in a little bit. Okay, anyway, so here's an AC source. What we'll be considering is we are getting a single frequency source and a pure sine wave. Okay? So that will be our source. So our source, the source voltage, and this is the electrical symbol for an AC source. And here's the amplitude of the source. So by the way, you're getting 120 volts out of it, and that's called RMS voltage. The amplitude is 170 volts. Okay, so sine omega t, omega is 2 pi f, and f is 60 hertz. Yes. So what you're getting out of the wall is that. So you're getting a voltage like this. Okay. All right, so now what this chapter is about is we're going to apply an AC source to our circuit. So here's an example. We're applying an AC source to this circuit. So this is our load. And then you'll do a circuits course. You'll want to know the current through each element. That tells you how much power is being delivered to each element and so on. So that's a different thing. All right. So this is the load. Right now, what we're concerned with is the following. So here is the source that you have attached to this circuit. We want to know two things. What is the amplitude of the current flowing out of the source? And we want to know this phase factor. So those are the two things we want to know. Okay. The amplitude of the current and this phase factor. Okay, now I'm going to summarize the entire chapter on this slide. Okay, so let's start off with the DC circuit. Okay, so I'll remind you of things. So we'll keep things simple. And ask me questions if you. Yeah. So for this DC circuit, the current was the current was V over R. Okay. So in this case, the current will be V over, so here the current is the amplitude of, so instead of V, we're replacing the amplitude of the and Z sine omega t minus V. All right, so this expression will get expressions like this, and this will look exactly like that. And so the resistance of the circuit is generalized to something called the impedance, and that's denoted by Z. Okay, so Z is the impedance. Okay, so that's one of the things we want to find. Here is your circuit, and what is the impedance of this circuit? Okay. Now we won't do it for this one. We'll do it for some simple cases, but that's the generalized term. Okay, what is this fella? Okay, what this fella is telling you is, you see, if you look at this equation, this is telling you the current is not in lockstep with the voltage. So in this circuit, if you increase the voltage, the current increases instantly. For a general circuit like this, when you increase the voltage, the current is not increasing in lockstep. That's the phase difference. Okay? And that tells you an important thing. So let me show you what that tells you. Yeah. So what is the power delivered here? The power delivered here is V times I. That is the energy delivered per second to the load. In this circuit, okay, now I'm going to erase this because I need some space. In this circuit, the power delivered, average power, because for an AC circuit, things are changing with time, so we take the time average. It's E max, I max, divided by 2 cosine phi. Okay, let's make sure we understand this. So this expression looks exactly like this, E max, V max, except that they have these factors. Okay. So we want to make this look more like that. So what we'll define is, we'll define E RMS, RMS being root mean square, E max over root 2, and I max, I RMS equal to I max over root 2. So now we'll write this as E RMS, I RMS cosine phi. All right, one of the things you'll see is we want to write all our expressions just like for the DC circuit. Just a second. All right, so this term is almost exactly like that except for this extra term. You can't escape that. Okay. Now let's look at what this means. All right, what is the, so if this circuit were purely inductive circuit, if this load had only an inductor, then phi, so for this circuit, okay, for purely an inductive circuit, phi would be pi by 2. Okay, what does that tell you?
It shifted by pi over 2.
Okay.
So the power's delivered that much.
Cosine pi over 2 is 0.
There you go.
So it's instant.
So cosine pi by 2 is 0. If your oven was a purely inductive oven, it won't cook your pizza. So you see how important that factor is? If this circuit is purely a capacitive circuit, phi would be minus pi by 2. Is your pizza being cooked?
Still 0.
It's 0. So when is your pizza being cooked? When it's a purely resistive circuit, that's when phi is 0. That's when your pizza is being cooked. Okay, so this will be very important. Okay. So for instance, if this was Hoover Dam and this is your city has all kinds of inductors and capacitors in it. If you want maximum power delivered to your city, what is it that you want to do?
Make the 0.
Make phi 0. And we'll show you how to make phi 0. All right, so you've seen it. All right, do you guys understand this? So what we're doing is we're connecting an AC source to your load, and there are two things that we're looking for. So these are the two things we want to find. Imax is Emax over Z. Z is your impedance, and then the power factor is phi. So for every circuit, what we want to do is we want to find these two things. That's our goal. What is Z? The impedance of the circuit. Okay, impedance is just a generalization of the resistance. Okay, and what is the power factor? Okay.
Professor,
Mm-hmm.
do we ever get into the specifics of how multi-phase AC circuits work? And like how the phase change affects it that way?
Well, for instance, we won't talk about it, but so in your house, FPL sends you, this is one live wire, and they'll send you a 180-degree out of phase wire as well. So when you want to operate your TV, you just feed it this signal, but when you want to operate your washing machine, you feed both of these guys. So what you're getting is a voltage, a wave of amplitude twice that 340 volts, 240 volts.
Okay. The
So-
only reason I asked is that the generator I work